Hello, hello, hello. Can you see me? Can you hear me? Are we there? Greetings. Who's in? Make yourselves known. Oh, hello, Yashi. Greetings, Yusuf. Hello, Path. How are we all doing? Hope you had a good summer. Can you see me and hear me all right? All good, thank you. Yeah, had a nice little rest. Good, good. Thank you, Path. Let me know. Good stuff. Right. Some of you have seen me before, some of you maybe haven't. This is just a little taster lesson. Give you an idea of what Year 12 physics is going to be like. That's going to be me teaching it this year. So I'm that guy, Dario Babavasiliou. I teach maths and physics here at my headspace. And yeah, I've got a PhD in physics. So hopefully, oh, greetings, Isa. Hello, hello, hello. Hopefully that'll do. But if you know anyone who might benefit from this, who you know has taken A-level physics, and in particular, anyone who's taken A-level physics and isn't sure about it, by all means, greetings, Arifa. Just copy the link, send it to them, ping it off to them. We'll wait a couple of minutes, see if people want to join. Greetings, Melon. Hello, hello, hello. Yeah, get your mates involved. Not a problem, Navneet. Oh, sorry, Isa, we said, right? It's going to be a bit of these names, especially when people's names are not their actual names. But never mind, I'll do my best to remember. How are you feeling this day? Give me a 1 to 5. 1 is terrible, 5 is great. Oh, it's a good solid 4. I like it. Oh, first day of year 11. So what are you doing here then? Just trying to get ahead of the curve, I guess. That's a strong showing path. Yeah, I thought. Wait, so you're just here to say hi? You're going to be doing the year 12 course then, Yashi? And you, Isa? Are you doing year 12 physics or year 11? Oh, all right, nice. Well, see what you think of it today. See what you think of it today. It's a bit of a jump from GCSE to A level, but you know, it's still physics, so it's still good. Should we make a start? If you're ready, say ready. Good stuff. Let's do it. Yeah, don't worry, you get used to it. You get used to it. So, what are we doing today? I mean, first of all, I just wanted to talk about what physics is and kind of what your reasons might have been for picking physics, why you're thinking about. I mean, if you're doing GCSE, obviously you have to do it, but presumably to be here, you're thinking ahead to A level already. So, what is physics to you? Why did you pick physics, or why are you thinking about picking physics? Study of the world around you and how it works, study of energy. Okay, you're here because it might lead to engineering. Okay, so physics might lead to a bunch of careers. Study of the world. Okay, enjoyed it at GCSE. Nice. So matter, energy, the world. Right, I'll give you my own definition. So the word physics itself in Greek means nature, right? So physics means nature. And you might be thinking, hang on a minute, which is the science that you might think deals with nature? I mean, if you think nature, maybe physics isn't the first thing that comes to mind, right? You might be thinking biology, except biology really is living nature. nature, we have to kind of broaden our minds and think beyond just living things because, like, a rock still is part of nature. Nature is everything all around us. So when we say nature, we mean absolutely everything. You know, stars and planets, they exist naturally. We didn't put them there. They're there, but we definitely wouldn't try to understand them using biology. We definitely wouldn't try to understand them using chemistry, but they're still part of nature. So really, we're going beyond just living things to absolutely everything, alive or not. Now, here's a beautiful definition of physics that a friend of mine told me. I studied physics, but I definitely wasn't the best physicist in my class. In fact, most people, I did pretty well. I got my first, but I'm not sure back then I knew how to think as a physicist. So I asked this friend of mine, what is physics to you? And this friend, who definitely was a real physicist and one of the smartest people I've met, said, physics is a cartoon version of reality. Anyone that was in my year 10 course, you might remember me going on about this about a year ago. It's a cartoon version of reality drawn using maths. Yeah, exactly. Remember? So we're going to get into that a little bit deeper now, right? That's why I've got a little cartoon here. This is, by the way, who is this guy in the cartoon? Does anyone know? Apple about to fall on his head. Oh, that is man-like. Sir Isaac. There he is. Yeah, you probably do. Neil does, crying. Greetings, Kumar. Yeah, that's Sir Isaac Newton. So today I'm going to show you just one little example of something where we make a simplified version, a cartoon version of reality using maths. Now, thing about cartoons, yes, they're simplified, but they still give you an idea, right? This might not look like a realistic drawing of a person, but you can still tell it's a person. It's still got the essential features of a person, like a nose and two eyes and, a finger, whatever. So the models that we're going to be dealing with in physics might be simplified. They're not perfect, but they definitely give us an idea of what real things really do. So let's get into it. If you're ready, say ready. Good stuff. Yeah, love it. So here's an example. We're going to jump straight into it. We're going to use some graphs, some motion graphs, right? Now, if you've done GCSE, you would have seen these. If you've only done year 10 of GCSE, you might not. So let's focus on this graph here on what's that? That's the right-hand side of the page. We've got a velocity axis. No worries, Isa. What does velocity mean, guys? Very good, Yashi, very good path. Velocity means speed with a direction. Now, simplification number one. In today's lesson, we only have two possible directions. What directions do you think we might have in today's lesson? If we're thinking about the simplest possible way that we can describe movement, if I told you there's only two directions we could be going in, which ones might they be? Yeah, we could call it left and right, right? Just any two opposite directions. We could say left or right, or we could say forwards or backwards. In fact, we're going to call our directions the positive direction or the negative direction. And that could mean whatever you want it to mean. It could mean east, west. It could mean north, south. It could mean forwards, backwards. It could mean up, down. Just two opposite directions. And then time here in seconds. Now, one thing I want you to note, look at this unit here. Now, in GCSE, what was the unit of speed or velocity? How did you measure how fast things were going in GCSE? Hmm. Very good, Yashi. We used to call it meters per second, m/s. Now, what do you see here? Here we see ms with a little -1. Now, you maybe remember from GCSE maths that if you have a power of -1, that's actually the same as a division. So this thing, ms -1, means exactly, it's a reciprocal. Very good, Path. So this thing actually means the same as m per s, right? S to the -1 means dividing by s, so m/s. But in A-level physics, we call it ms to the -1. It helps us keep track of things when we're dividing by too many things. And careful, Yashi, because the -1 only acts on the s, not the m. So we have a velocity, greetings Isa, we have a velocity time graph here. Now, look at this. We start from an initial velocity of u, and we end up at a final velocity of v. Okay, so let's start writing that down. U is the initial velocity. What does the word initial mean? It's at the beginning, right? The starting velocity. And v is the final velocity. The way I remember them is their order in the alphabet, right? If you go A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V. U comes before V, so U is the initial, V is the final, right? And it takes a time t to get there, right? This is our model. This is our simplified model. This could mean that someone just starts going at a certain speed and then speeds up in a certain amount of time. Cool. In reality, I mean, they might not speed up completely evenly, right? It might be a little bit more wibbly wobbly. This might be reality. And the blue line is actually our cartoon version of reality. It's a simplified model, but it will do for us. Right? We just draw a straight line because it's easier. It's easier to deal with and it's good enough. Now, the acceleration is the gradient of this velocity time graph. How do we find a gradient? Very good, Yashi. It might be in a long summer, but some people are switched on. Very good, Path, absolutely. So, our gradient here, our acceleration, yes, Kumar, nice. Yeah, good, Abdurrahman. So, acceleration equals the change in velocity, exactly, the change in the vertical thing divided by the change in time. Correct. Change in velocity over change in time. So we might write that as A for acceleration. Now the change in velocity, you're going from u to v. So the change is v minus u. And the change in time, you're going from 0 to t. That's a difference of t. Oh, hang on a minute. That looks like an equation to me. And in fact, this equation was in GCSE physics. But that's where it comes from. It comes from this little cartoon graph. And it allows us to work out accelerations. Nice. So we found an equation for acceleration. Now, here's where it gets just a little smidgen more complicated. The area under the velocity time graph gives us the displacement. This word displacement essentially means, have you heard it before? Do we know what this means? It's not, you can think of it as a minimum distance, Yashi. How far an object has moved with a direction, right? It's a bit like velocity compared to speed. This means the straight line distance with a direction. Distance from starting point. Yes, exactly, Path. It's a vector quantity. I've been trying to avoid the word because I haven't actually told you what a vector is yet, but we will do all of that in the year 12 course. Distance from starting point with direction. So if the area gives us the displacement, and displacement, don't ask me why, gets given the letter S. How would I find the area under this graph? Essentially everything that you see here that's shaded light blue. How do I find this area here? Okay, have you come up with that path? How would I do it? Right, very good. The shape is a trapezium, right? Excellent. Or you can think of it correct mundane. You can also think of it as a rectangle plus a triangle. Either way you do it, you're going to find this. Let's do rectangle plus triangle. I prefer that because I always get confused trying to remember the formula of a trapezium. I mean, maybe you're smarter than me, you always remember it. I always prefer to break it down to simpler shapes. So here is a rectangle. The height is u, the length is t. So this is u times t. Right, it's A level now. We're not going to write multiplication signs. We're just going to put letters together. We know that means multiplication. Here's a rectangle. Formula for a rectangle we know is half times the base is t. The height is v minus u. So it's half times base times height. So that means that our total area is going to be ut plus 1/2 v minus ut. And it turns out, let's do a bit of simplification, right? So here's ut, that's fine. Let's multiply out these brackets. So I've got v times t, so ut plus half times v minus half times u. But then I'm going to multiply out that t as well. Exactly, Yashi. ut plus half v times t is half vt minus half u times t, half ut. If this is feeling like a maths lesson, well, like I said, maths is our tool that we're going to be using. So, we're going to be very comfortable with algebra. We're going to be using it quite a lot. So we've got ut plus half vt minus a half ut. Well, half of the ut is taken off the ut. We're going to end up with half of ut plus half of vt. And to put it all together, that ends up being s is half of u plus v t, which some of you have been screaming out for whole minutes already. Oh, look, that looks like a formula that allows us to find distances now. Okay, so s equals half u plus v t. Nice. Well, Yashi, I'm going to try and make sure that you know how to derive them so that if you understand where they come from, they're much, much, much easier to memorize. These aren't just coming out of anywhere. That's what I'm trying to show you. And if you have practiced finding them from the graph, you'll be able to just sketch the graph, 2 minutes, bam, got them. So let's put them to good use now. A ball starting at an initial speed of 10 meters per second. So that means that initial speed was u. U is 10 meters per second. Let's get all of our facts straight, right? Let's get everything down. Accelerates for 2 minutes. So my time is what? What am I going to write down for the time, guys? Yeah, good. 2 minutes won't do. We need to convert it to seconds. 120 seconds with an acceleration of 1.5 meters per second. A is 1.5 meters per second squared. Notice instead of doing m slash s squared, we call it ms to the minus 2. Okay, again, that's A level units. And we want to find the velocity. Which of those two formulae are we going to use for the velocity? We have u, a, and t, and we want to find v. We're going to use the first one or the second one? We're going to use the first one, right? We've got everything else. So let me put everything in, do a bit of rearrangement. So I'm going to say, so A is 1.5. V is what we're trying to find, V minus 10 over 120. All right, who's going to be the first to solve this? Who's going to tell me what V is? come on. Let's see. Very good, Yashi, very good path, right? So multiply both sides by 120. 1.5 times 120 is 180 equals V minus 10. So 180 is V minus 10. So V is 190 meters per second. That's a pretty fast ball, but who cares? That's what the maths told us. That's what the physics has told us it's going to do. Okay. B, find the total displacement of the ball after the same 2 minutes. So how are we going to do B? Second formula, right? Let's see. So S equals, exactly, find the area, or just use the second equation, which really means find the area. I mean, we could write down values on the graph and find the area. If you prefer, if you're a visual person, nothing wrong with that. You could write U is 10, V is 190, and T is 120. And there you've got a little trapezium with a short base of 10, a long base of 190, and a height, really, of 120. You could do it that way. Or you could just use the formula, which does the same thing. So we're going to say S equals 1/2 of U is 10, V is 190, and T is, we said, 120. So 10 plus 190 is 200. And what does that give me? Yeah, that gives me like 12,000 meters. So, okay, it's a fast ball. It's traveled very far. Does that surprise us? Well, if it's going at 190 meters per second, by the end of it, it's probably going to whiz pretty fast, right? Nice, guys. You just did your first bit of A-level physics. If you're ready to turn the page, say ready. All right. So it turns out that what I've just shown you here is part of a bigger structure of things called suvat. Right? We call it suvat because it literally, we have S. Who remembers what S stood for? In fact, here they are, SUVAT. What did S stand for in a funny roundabout way? That was the displacement. Displacenet. I'm going to call it displacenet from now on. That's the displacenet. U is the initial what path? Not initial speed, it was the initial velocity. Yeah. Turns out direction is really important here. V is the final velocity. A is the accélération. And T is the time taken. Now, the idea is that we have these 5 quantities. And what we're going to do using the suvat equations, we've already seen 2 of them. Now, the 2 that we've seen were, what was it? It was A equals V minus U over T. And the other one was S equals V plus U over 2 times T. By the way, this dot in the middle means a multiplication. That's something that you might see. You'll definitely see that in maths. What do you notice about these 2 equations? We've got 5 variables here, S, U, V, A, T. What do you notice about these 2 formulae? They use the same values, but do they use all the same values? How many variables are there in each one of these formulae? How many variables are in each one? Very good, Kuma. One's missing. Which variable is missing from the first one? The first one is, let's see, we've got U, we've got V, got A, got T. There's no S. This one is displacementless. And which variable is the second one missing? The second one's missing the acceleration. Now, I'd love to sit and show you where these other ones come from, and do you know what? Maybe I might even. But long story short, the moral of the story is there's how many more are we going to need? If each one is missing one variable, how many more equations do we need? We've got one without S, we've got one without A. We're actually going to need three more, right? We need to have one missing each of the variables. There's going to be one with no U, there's going to be one with no V, and there's going to be one with no T. So the idea is, if we know three of these variables, we can find the other two. That's our really important principle. Why are they missing? Because it makes things easier, Abdurrahman, and also because they're all linked. Okay, so it turns out we don't need all five at the same time. So, Parth, what you've told me is actually a rearrangement of the first one, the one with no S. It turns out the other two are, the other three, sorry, the one with no U is S equals VT minus 1/2 AT squared. The one with no V is S equals UT plus 1/2 AT squared. Kuma, because we don't need it, it turns out. And knowing three of the variables, Kuma, is easier than knowing four, right? The idea is that if you know four of them, you've actually solved the problem exactly. We don't need all of them at the same time. If you know four of them, you've solved the problem. You can find the other one. Don't worry, Yashi. These are going to become your best friends. You're going to know these by heart. And then the last one, the one without time, the one I call timeless, this one is actually in GCSE triple as well. V squared equals U squared plus 2AS. But it's actually part of all of this. So the first one and the last one are in GCSE. The other three come from looking at the area, actually. Yeah, this one is the one that you used to use for stopping distance and thinking distance in GCSE. This was the stopping. Mundane, the dot is a multiplication sign. We use a dot instead of a cross so it doesn't look like an X. So this one was the stopping distance formula. So if we know three variables, we just need to pick the formula to find the others. Let's have a look at some examples. Right, I know this might be a bit overwhelming, so what I recommend, take a little screenshot right now so you've got them. Okay, so you can refer to them because I'm going to be asking you which one we should use in any situation. Let me number them as well. When you've taken your screenshot and you're ready to move on, say ready. Nice. Why are they missing? Ready. Abdurrahman, I'll show you how they work, and as we get to use them, they'll make more sense. Maybe after we've used them a bit, I'll show you where the other three come from, actually. It's quite nice maths, but I also want to sort of focus on the physics and solve some problems. So here we go. A skateboarder traveling in a straight line up a ramp experiences a constant deceleration 0.5 meters per second squared. His velocity at t is 0 is 8 meters per second. So we write down the following suvat situation. All right, let's call it a suvatuation. Now, where have these numbers come from? Notice u is 8. What part of the question tells us that u is 8? It's this bit here, right? It says the velocity at time is 0. Time is 0 is the beginning, right? At the beginning, right? So that's the initial velocity. The initial velocity is a. Boom. Okay. And then what about, why has this got a minus sign in front of it? Why is the acceleration negative? It's a deceleration. Right, exactly. It's an acceleration backwards. Remember, our only directions are forward and backward. That's our model. Good, it's slowing down. Deceleration means a negative acceleration. And then v is 0. Essentially, I want you to imagine this. You're rolling up the ramp. You're a skateboarder rolling up the ramp, and then you slow down, and eventually you stop at your maximum height. So the final velocity is 0. You stop a little bit. So number one, how long will it take for him to reach the maximum height? So we've got u, v, and a. Which variable are we trying to find? If the question is how long, what are we trying to find? We're trying to find time, right? So actually, which one are we not interested in? We're trying to find time. We have u, v, a. So we're not interested in s. So we need the formula without s, because we're not interested in s. We don't care. It doesn't need to be involved in the formula. So we need the s-less formula. Which one was the s-less formula from the screenshot that you took a minute ago? Nice one, Path. The first one, a equals v minus u over t. All right. So let's put in the numbers and let's work it out. So a is minus 0.5. V minus u is 0 minus 8 over t. All right, who's going to solve it? Oh, Path's there already. See if we all agree. Nice one, Yashi. Good. Yeah, so this is swapsies. If anyone was in my GCSE maths last year. Yeah, so t is minus 8 divided by minus 0.5, 16 seconds. Nice. All right, number 2. How high up the ramp can he go? What are we trying to find? What are we not interested in? We need displacement, so we need s. Now, actually, let's write them down. We've got everything else, right? We need displacement, so question mark, but now we know 8, we know 0, we know minus 0.5, and we know 16. However, I would not use a formula using time. Exactly, Yashi. Why would I ignore my value of time that I just worked out? I just worked it out. Why wouldn't I use it? It's true that you only need 3, but why don't I use time as one of the 3? I might say, oh, do you know what? I don't like decimals. I don't like 0.5. Correct, Kumar. Kumar says it's more accurate if we use the given values. These are given, while this is what we call derived. That means I worked it out. Why do I trust given more than derived? You could be wrong, right? Trust no one, especially not yourself. So there might be a mistake. Probably isn't. It was quite easy. It wasn't that difficult, but you never know. So this one might be wrong. So we don't use it. Wherever we can, we use only numbers given in the question. We try to avoid putting our own results back in formulae. Trust nobody, but yeah, but maths teachers make mistakes all the time. So really trust no one. So which formula is it? Which one is timeless? Which formula is timeless? So need t less the last one, right? So it was what? V squared equals u squared plus 2as. Yeah, so let's put that in. Sorry, I forgot to write in green, and now it clashes what we were writing before. 0 equals u squared is 8 squared plus 2a is minus 0.5 and s is whatever it is. All right, who's going to be the first to tell me what s is? Yeah, but Abdurrahman, don't worry, you're going to use them so often. And actually, you learn about these in maths as well, that you will memorize them. So 2 times minus a half makes minus 1. 2 times a half is 1, of course. 64. Oh, that's an easy equation. So S is 64 meters. And I like that you put the units path. Very good. You're behaving like a physicist. Yeah. So, ready for the next one? Nice. All right, let's go. So we have a particle is moving in a straight line with a constant acceleration of 3 meters per second squared. So we're starting to write down our little suvatuation already. S-U-V-A-T. And let's write down the values as we find them. Constant acceleration 3. So A is 3. At a time t is 0, the speed of the particle is 2. So what am I going to fill out with that information? At a time t is 0, the speed is 2. Very good. U is 2. Do you know what? It's so easy to look at that and think t is 0. Let me put in t is 0. That's not what it's telling us. It's telling us about the initial speed. So actually, it's u that it's telling us about. And then find the speed of the particle at t is 6. That's what t is. So what are we trying to find? What we're not interested in. So we need which one? We are not interested in which one? So which formula we're going to use? Yeah, we need V. We're not interested in S. So which is the formula? The S-less. Very good. Formula is the S-less one. That's the first one. A equals V minus U over T. So 3 is V minus 2 divided by 6. So what's V? 20. Good. Multiply out the 6. 3 6 is 18. Add the 2. V is 20. MS minus 1. Nice one, path. Only one writing in the units. All right, number 2. S-U-V-A-T. So find the displacement. So S is now what we want. U is 2. I don't trust myself, so I'm not going to use V, but I know that A is 3, T is 6. Which formula am I going to use now? Yeah, now we want the V-less, which is S equals UT plus 1/2 AT squared. Greetings, Sugath. Good to see you. Yeah. Always welcome. So S is going to be U times 6 plus 1/2 times 3 times T squared, 6 squared. What does that make, guys? Units path. It's unlike you not to write them down. Good. 2 sixes is 12. Half of 6 squared is 36. Half of 36 is 18. 3 18s is 54. Oh, can't wait, Suga. It's going to be great. 66 meters. Nice. All right, I'm going to put it to a vote now. In fact, let's do a little poll. Let's see, little poll. Your options at this point are the following. We can either do more practice using suvat, or I can show you where the formulae come from. So let's see. Majority wins. Democracy, tyranny of the majority. Oh, it's overwhelming. It's overwhelming. I love it. You've picked the right one. What can I say? That is absolutely the right choice. Where do these formulae come from? With an 83% majority, boom. Okay, 7 votes, but whatever. That means 5 people have got the right idea. And the other 2, don't worry. We're going to derive them quickly and then it will be okay. So, oof, God, it's a bit of a mess, isn't it? So let me just put in a new page, right? We're going to need a blank page here. Just give me a second. No photo. Don't need photos here. Just cartoons. Okay. So, here's what's going on. We said that this suvat came from this picture, and this picture is super, super, super important. This is where everything comes from. We start from an initial velocity of u, we end up at a final velocity of v. So this is your velocity. And we start from a time of 0 and end at a time of t. Right? So here's our model. Here's our cartoon version of reality. Now, we already saw how 2 of the formulae came from this. Who wants to remind me how 2 of those formulae came from this? Gradient, very good. The gradient gave me A equals V minus U over T, and the area was the displacement, right? So S was V plus U over 2 times T, okay? Now, let me show you where the others come from. If you remember the Euler and Wheeler formulae, here they are, they're also S equals. Do you see that? They're also something to do with displacement. Okay, so that means they should have something to do with the area. Now, this area here comes from thinking about it like a trapezium, right? You can see we've clearly got short base u plus long base v divided by 2 multiplied by height t. Now let's break down the area differently. Let's break it up into a rectangle, ut, and let's see what this triangle is. Now this triangle has a base of t and a height of v minus u. Are you with me? If you're with me, say with you. If you're not with me, write a question mark. All right, cool, cool, cool. Nice, nice. Now, where have we seen v minus u before? Oh, that means you're not really with me, Sugath, but bear with me, okay? Where have we seen v minus u? There's actually a v minus u elsewhere on this page. In the first equation, here's v minus u right here. So actually, I could do a cheeky little rearrangement and say v minus u, if I multiply the t across, at is v minus u. Do you see that? I've literally just moved the t to the other side because it was dividing, it now multiplies, right? With me or question mark? Cool. So I can just replace v minus u with an at. So what's the area of this triangle now? The rectangle is definitely ut. But what's the area of the triangle? Good. It's almost, Yashi. Area is half times base times height, right? So it's half times t times at. Half times base times height. Well, that's half a t squared, right? You've got a t here and a t here. So the area could also be S equals rectangle ut plus triangle half a t squared. Oh my God, that's the v-less formula. We found it. Nice. All right, let's see what else we can do. Now check this out. This is even cheekier, right? Watch this. We could also say, oh, it's about one model of how things move, Sugath. You could write delta U Kuma. Correct. Correct. Here's another way you can think about it. Now, we said it's like a little rectangle plus a triangle, but surely we could also think of a big rectangle minus a triangle, right? It's like a big rectangle with a triangle cut out. So we could also say S equals the big rectangle, VT, and we've cut off this triangle, which is half AT squared. Oh, that was easy. So in other words, we're either thinking this is a small rectangle plus the triangle, or we could think of it as the big rectangle with a triangle cut out. So there's 4 of our 5 formulae. Ready for the last one? If you're ready, say ready. So we said this one here is S-less. This one here is A-less. This one here is V-less. And this one here is U-less. So we need a timeless one, right? So all we need is one formula with no time. Problem is that time is actually one of the axes of this graph, right? So time is kind of important. It's quite difficult to eliminate time unless you do a little mathematical trick. So here's the mathematical trick. You notice that you've got time as a denominator here and time as a numerator here. How could you cancel out a numerator and a denominator? Yeah, we could multiply. Greetings, Rubik's Cube girl. We could multiply. So look what we're going to do. We're going to multiply all of the S-less formula by all of the A-less formula. So we're going to go A times S equals V minus U over T times, oh, good to hear, Rubik's Cube girl, V plus U over 2T. Right, so I've literally multiplied the two formulae together because I know if I've got a t in the denominator and in the numerator, they'll cancel out, and there's my t-less. Now, how can I simplify this? On the left-hand side, I've got a times s, which is as. On the right-hand side, I've got v minus u, v plus u over 2. So what do we do? it's being multiplied, Rubik's Cube girl, so I wouldn't subtract it. Multiply everything. How do you multiply this out? This is actually a special multiplication that you maybe have seen before, especially if you've done quite a bit of algebra in your GCSE maths. This is a factorization you should recognize. Look, v times v, v times u times v, u times u. So that is v times v, v squared. V times u plus uv minus u times v minus uv minus u times u minus u squared over 2. Zack, zack. Look, you got plus uv minus uv. Oh, hang on a minute. As equals v squared minus u squared over 2. We're actually basically done, because what happens now, you multiply this 2 up, that's your 2as, equals v squared minus u squared. All you need to do is bring the minus u squared to this side, and you've now got v squared equals u squared plus 2as. And that is your timeless formula. Okay, so it's pretty neat, and I recommend you practice this a few times, because once you know where they all come from the graph, it means you don't really need to memorize them. They're not this meaningless jumble of algebra that you just have to memorize. Yeah, I mean, I like this. This is a neat little thing. You know, it's right at the beginning of the A level, but it's one of my favorite things. So I don't think, no, you definitely don't need this for year 10 SUGAF, although the 2 of those formulae are in the GCSE. The very first one, the one under where it says gradient. Oh, I'm doing this because this is a year 12 taster Rubik's Cube girl. This isn't for the year 10 course, this is for the year 12 course. Well, it's okay, you know, if you're joining us in year 10, you're looking forward to this, then great. So we've been here almost an hour. I was thinking maybe this is a good enough introduction. We're going to get lots of practice of this in the year 12 course. Guys joining the year 10 course, all the best, you know. You don't need to run before you can walk, but you know, I'm glad you're